on the fourth day of this STTP, the second session on the topic of Earth energy. We are going to start. Uh, the expert of this second session, is Dr. R.D. Patel, sir, who is head of the Mechanization Department at BN Institute of Technology, Vallah Vidyanagar. He is currently serving as head of the department, and he has done his PhD in numerical and experimental analysis of Buret tube heat exchanger performance from Charusat University, Changa. He's he has published 10 plus research papers in reputed national and international journals and published a book on Bureau air conditioning system in Lambert academic publications. Dr. Adi Patel sir is also recipient of many prestigious awards, which include Best Polytechnic Teacher Award in Gujarat State for the year 2014 by Indian Society for Technical Education, New Delhi, and Gaurav Puruskar 2020 by Charute Vidya Mandal. And recently, he has received Excellence Award by the Institution of Venues India. He is also IST National Executive Council member for the term 2020 to 2024 and chairman of IEI Vallah Vidyanagar Local Center for the term 2020 to 2022. He is very much associated with Gujarat Tech University and former Dean Diploma Section and coordinator of Zone 3 and member of Board of Studies of Diploma Engineering. Dr. R.D. Patel sir has successfully completed two research projects from Gujarat and AICTE. He has received many financial grants from various funding agencies like Gujarat, AICTE, IST, IEI, and many more. He has organized 50 plus programs for students and teachers like FDP, STTP, workshop, conferences, students program, etc. for the betterment of technical education. He has filed two patents in the field of refrigeration and air conditioning engineering. Apart from Bureau energy conservation, his area of interest include refrigeration and air conditioning, thermal students startup project. On behalf of all participants, I welcome you, sir, and I request you to enlighten us with your experience and knowledge. Dr. Adipede, sir, please, you may start your session.
Thank you, Hirar. I welcome all the participants and very good morning to all of you. I think you all enjoyed all the session of this AICT IST sponsored FDP on energy conservation and energy management. So now continuation of this energy management and energy conservation. I talked on earth energy. So first of all, I share my presentation. Yes, Hirar, it's visible.
Yes, yes, sir, complete. Okay.
Yes, it's visible.
Yes, yes. Now, first of all, what is the earth energy? Earth energy, before the discussion of this topic, I saw my outline of my presentation. In first section, I present introductory part of earth energy and objective of this presentation. Numerical and analytical analysis of earth or buried tube heat exchanger are discussed in the second section. Discussion of experimental analysis is included in the third section. And finally, I discussed the result and conclusion of my research. Now, first of all, what is the earth energy or buried energy? Actually, earth energy is synonyms of buried energy. The fact that the year-round the temperature at 3 to 4 meter below the Earth's surface remain virtually constant throughout the year. That makes it potentially useful in providing building with air conditioning. That means from the ground level, approximately 3 to 4 meter from the surface, the temperature of Earth at approximately 26 degrees centigrade is constant throughout the year. And this temperature or this energy is used for the air conditioning of a building or room. So throughout the year, the outside temperature in Indian climate is varies from 20 degrees centigrade to 45 degrees centigrade. In season of winter is approximately 15 to 20 degrees centigrade at this climate condition, and it's maximum up to 45 degrees centigrade in summers. But while the soil temperature at a lower range only 24 degrees centigrade to 28 degrees centigrade. So it depends on the ambient temperature of the locations. The buried heat, the systems can be used to provide the cooling during the summer, soil as a heat sink, and heating during the winter, where the soil work as a heat source. So basically, the earth energy is used for the heating purpose as well as the cooling purpose in the summer as well as in winter seasons. So first of all, what is the earth tube heat exchanger? Because this heat exchanger is a very important role of the energy transfer from buried depth to the building or room. So the earth or buried tube heat exchanger is a system which decreases the interior temperature of a building during the summer, and it also able to increase during the winter by using the thermal potential of the ground. So this pictures is clearly show how the heat exchange from buried depth to the room with the help of one simple blower at a very low energy consumption, and this air is conditioning at buried depth, and this conditioning air is passed to the room or building. In short, the air is either cooled or heated by circulating the underground, means underground means that's a buried depth, in horizontally or vertically buried pipe at a specific depth, and this specific depth is called a buried depth. It is basically the geographical condition of our Gujarat state, especially the 3 to 4 meter depth is a buried depth, and it is very special, very suitable conditioning buried depth for the heating and cooling purpose of the building, and this air will be used as a conditioning purpose. So these are one simple flow diagram of air to how the ambient air is cooled the building or the room. Now the classification of the heat exchanger. So first of all, the classification of a heat exchanger based on this alignment. So horizontal buried tube heat exchanger, and second one is the vertical buried tube heat exchanger. Now in horizontal buried tube heat exchanger, the major portion of this heat exchanger horizontally buried at buried depth. Otherwise, the principle and working of the both heat exchanger are same. In same as the vertical buried tube heat exchanger, the heat exchanger major part buried in vertical condition from 3 to 10 meter from the ground surface. So basically two major classification of the heat exchanger. First one is the horizontal, and second one is the vertical buried tube heat exchanger. Now, what is the objective of this heat exchanger or this research? So first one, to review the state of art of the buried tube heat exchanger. Second one, the numerical, analytical, and experimental analysis of this BTH or earth tube heat exchanger for optimizing the performance. Second one, to determine the exact tonnage capacity of the heat exchanger for specific load in cooling as well as the heating mode with respect to design and material of heat exchanger. Next one, investigate the various performance enhancement method that could be employed to optimize the thermal performance of buried tube heat exchanger. And next one, to develop a thermal model for simulating the energy performance of a heat exchanger. Finally, to validate the result of simulation with a real experiment setup of buried tube heat exchanger, and to reduce the high consumption of conventional air conditioning system load, means as we are using the conventional air conditioning systems replaced by this buried tube heat exchanger, and reduce the energy consumption in residential building as well as in commercial building. Then this improves the efficiency of HVAC systems. To design the parameter that impact the performance of heat exchanger, and buried tube heat exchanger uses the space conditioning for human comfort. So these are the objective of our research. Now, contribution and practical importance of this heat exchanger. The heat exchanger is applicable to the most building to reduce the energy of active heating or cooling system. The use of appropriate design of system may avoid the use of other conventional system. This heat exchanger can reduce the greenhouse gas emissions. The heat exchanger can improve the indoor thermal comfort, and the heat exchanger are cheaper and easier to construct than the active cooling systems. The maintenance and operation cost of buried tube heat exchanger are low compared to the other air conditioning systems, and the heat exchanger have long lifespan. Now, in my presentation, I derived analytical analysis, numerical analysis, and finally, the result of both the analysis, analytical and numerical analysis, is validated by experimental analysis. Now, first of all, I define the analytical analysis. Now, the thermal gradient of the soil. So, first of all, we find out the buried depth and the buried temperature for the air conditioning purpose. So, the buried temperature, that means the stable at certain depth, means buried temperature means the constant temperature throughout the air at a specific depth. So first of all, we find out the buried temperature and buried depth. So what is the buried temperature? The stable temperature at certain depth. As per the geographical condition, it may be vary from 3 to 5 meter. In specific at Anand region, it is at 3.5 meter. The pipe buried at depth could act as a heat exchanger. And during the year, it also depends on the ambient temperature. So ambient temperature is a very important role for the buried temperature. Second one, the heat transfer between pipe and soil. The important and effective design parameter of the heat exchanger. So buried depth, tube length, tube diameter, air velocity, air flow rate, tube material, tube arrangement, and location. So these are the very important or effective parameter for the design of this heat exchanger. Now the heat transfer mechanism around the buried tube heat exchanger are quite complex. So some assumptions generally considered for the modeling and thermal performance analysis of this heat exchanger systems. The pipe has uniform internal as well as outer diameter in axial direction. The soil around the pipe is homogeneous and its thermal conductivity has a constant value. So this assumption is very important for the designing purpose. And this assumption actually I taken from the literature review. Second one, the soil temperature near the pipe is not influenced by the pipe because the heat earth in summer we are using the as a heat source, as well as in summer in winter it is a heat sink. So the surface temperature of the pipe is uniform in axial direction. The convecting flow inside the pipe is thermally and hydrodynamically developed. The solar radiation is assumed to be constants. The surface temperature of the ground can be approximated to the ambient temperature equal to the inlet air temperature. So the inlet air temperature in the heat exchanger are almost constant to the ambient temperature of the air or surface temperature of the ground. Now analytical analysis. Some design parameter is there. The heat transfer depend on the surface area of the pipe. So major part of the heat exchanger depend on the heat transfer. So diameter and length is a vital role of the heat exchanger. So increase the length would means the increase the heat transfer, and that give the higher efficiency. After a certain depth, no significant heat transfer occur, hence optimize the length. After some depth, there is no difference of temperature as well as the gradients. So increased length also result in the increase the pressure drop, hence increase the fans energy. So economically and design factor needed to be balanced to the best performance at the cheapest or lowest cost. Now, the calculation are based on the approximation of the earth temperature, which varies with the time of the year and the depth under the surface. The heat transfer coefficient for the heat flow between the air, pipe, wall, and earth are estimated from material coefficient and geometrical parameters. The following parameters. So these parameters are calculated, which are calculated for the performance of the heat exchanger. The first of all, we determine the buried depth, which is the most important part of the research. The second one is the radial heat transfer from the pipe and heat exchanger. Second is a very important, same as the buried depth. The next one, the heat load for the buried tube heat exchanger. As we design or we install 1 tonnage capacity of conventional heat air conditioning system, same as some heat load is a major role of designing of the buried tube heat exchanger. Same as the mass flow rate of air, means air velocity is important. A velocity of air circulated in heat exchanger. Performance of heat exchanger means a COP is important. And now the simulation of buried tube heat exchanger. Now, first of all, some input data for the thermal design of 1 tonnage capacity heat exchanger for cooling as well as the heating system. So first one is the location. So first of all, I define the location where we install this heat exchanger. Second one, the capacity. The capacity, all the heat exchanger and all the analysis, analytical analysis and experimental analysis, and this analysis is for 1 tonnage capacity and to be cooled or heated space 1000 cubic feet. Now, inlet air temperature during the summer is 42 degrees centigrade. Inlet air temperature during the winter is 15 degrees centigrade. Buried temperature throughout the air, throughout the year is 28 degrees centigrade. Outer diameter of the heat exchanger is 110 mm. Inner diameter of heat exchanger taking the 102 mm. So thickness of the heat exchanger is 8 mm. Now fan power is also defined. Inlet velocity is also defined 15 meter per second. And I am taking the 3 material for the heat exchanger: RCC, copper, and PVC. So I am taking these 3 material for the analysis of analytical as well as the experimental analysis. So material part is very important for the heat exchanger. And this all the input data I am taking from the literature survey and from some experimental research. Now, input data, some constant I'm taking for the designing purpose: the thermal diffusivity, thermal conductivity, the thermal conductivity of material, as well as the thermal conductivity of soil. 3 types of soil: dry soil, as well as the wet soil, and the mixed soil between of dry and wet soil. So this data is from handbook, taking from the handbook for the designing purpose. Now, determination of the buried depth. The buried depth of the penetration depth can be determined from the concept to the semi-infinite solid, means single identifiable surface. So from the figure you easily what is the buried depth? So this buried depth is approximately 3 to 4 meter at Anand region, and approximately 28 degrees centigrade is constant temperature throughout the year at this buried depth. So the Earth can be considered as a semi-infinite solid because its one end surface feel the diurnal variation of temperature, while the other end at certain depth remain the unaffected. So determination of the buried depth from this simple thermal equation of in semi-infinite solid, and applied the boundary condition and using the separable variable of variable solution. So this equation can be reduced and find out the x. The x is the buried depth for the heat exchanger. Now, the Earth has a large thermal capacity. The effect of withdrawal of the heat or pumping of the heat in Earth will affect the Earth temperature at the buried depth. So this is a very important aspect for the buried depth. So this very stable thermal environment act as a heat source as well as the heat sinks. So this stable thermal environment can be coupled to the building, greenhouses, or any residential space using this heat exchanger to create the human comfort conditions. Now, radial heat transfer from pipe to the heat exchanger. Heat exchanger is considered as a hollow cylinder which is buried in the solid at buried depth. So exposed outer surface is surrounded by soil, and the temperature assigned to the outer wall of the pipe depends not only on the resistance between the hot and cold surface, but also on the capacity of the surrounding atmosphere to remove the heat arriving at the outer source. Some radial heat transfer from pipe to heat exchanger, where the convective heat resistance inside the pipe surface due to the flow of air. So our conduction, and the conduction resistance offered by the soil as well as the material which use calculated from these thermal equations. Now the total heat transfer between the air inside the tube and the soil is corrected by the following equations. So Q tube temperature, mean temperature minus out temperature by the resistance. The R total is the summation of three resistance across the heat flow path. So in figure shows the what is the R total, the resistance of three component. Now load, heating or cooling load for the buried tube heat exchanger systems depend on the place where we want to install the systems. It varies for different places like residence, classroom, greenhouse, or any restaurants or hospital. Mainly load on the occupants of the space to be cooled or heated. As a mechanical engineer, you all know the vent air is a very important role for any designing of air conditioning systems. As per the our air conditioning or HVAC systems norms, the vent air in restaurant or in hospital, the 100% vent air is used for the cooling as well as the heating purpose. But in case of domestic or our residential building, only 10 to 50% vent air is used for the conditioning of a room. So same parameter is used for the calculation of heat load. Now the heat exchanger has been designed to be cool or heat the residential space having 1000 cubic feet. Thus minimum heat energy to be removed by the system will be 3.5 kilowatt. Now, a mass flow rate of air in the heat exchanger. To transfer the heat from air to soil and from soil to air, certain mass flow rate has to be circulated. The mass flow rate requires depend on the total load required to be removed. If load required to be removed is more, then the mass flow will also be more. I think you got my point. The required mass flow rate can be calculated from the simple equation mCp delta T. So mass m is the mass flow rate, Cp is the specific heat, and delta T is the difference between inlet and outlet of the heat exchanger. So the simple heat exchanger calculation equation is used for the mass flow rate. Q is mCp delta T. Now, velocity of air. The velocity of air means flow rate of air is important. The velocity of air has profound effect of the heat transfer. The velocity of air depends on the total mass flow rate in the systems. If single pipe is selected to transfer the total heat load, the average velocity will be high, and it is calculated from the dense simple equation and density area into the velocity. So heat transfer coefficient, the estimate the air side convective heat transfer coefficient, where Nusselt number, Reynolds number, and Patel number are come in the calculation for the heat transfer coefficients. Now, the performance of the heat exchanger. As you know, the COP means the mCp delta T, means total heat divided by the work done. Means total heat means a refrigerating effect divided by the work done. So refrigerating effect means Q. So mCp delta T is a refrigerating effect, and work done, here work done by simple blower. So minimum work done means maximum COP, and maximum refrigerating effect is directly proportional to the COP. So this parameter is determined by dividing the energy output of a buried tube heat exchanger by electrical energy needed to run the blower fan at some specific temperature. And the higher the COP of the buried tube heat exchanger means more efficient buried tube heat exchanger is. Same COP formula is used as our we are using our conventional air conditioning systems. The value of the COP is always near to 1. Now, from analytical analysis, some outcome for the defining heat load means 1 tonnage capacity. So buried depth is 3 meter, mean temperature is 30 degrees centigrade, inlet area of the heat exchanger is 0.001817 meters square. A required total mass flow rate is 0.348 kg per second. Permissible mass flow rate in each pipe. Suppose we are using some series as well as the parallel pipe in designing of heat exchanger. So per pipe, the mass flow rate is 0.147 kg per second. A total pipe required to be removal of total is number 2. It may we can use 3 or 4 as per the design parameter. Now Reynolds number, Nusselt number, convective heat transfer, and finally the COP of the performance is 7.3 for the buried tube exchanger. So analytical outcome is important parameters for the designing of experimental heat exchanger. So temperature drop of air per meter length of pipe is considering the each buried tube heat exchanger is 10 meter long, and it is 40.80 degrees centigrade. Heat required for the removal of each heat exchanger per length is 175 watt. A minimum soil radius required around the pipe is 0.06 meter. Convective resistance due to the airflow, pipe material and surrounding is so here. Thus we can say that in case of PVC pipe, heat removed by the each buried pipe per meter of length will be 160 watt. So total heat removed by entire system will be approximately 3.3 kilowatt. Now, numerical analysis. Now, computational fluid dynamics is known as a powerful method to study heat and mass transfer for many years. Now, CFD simulation is the imitation of the operation of a real world process. It can be used to show the eventual real effect of alternative conditions and courses of the exchange. So nowadays, a CFD is a very useful tool for any mechanical analysis of any mechanical system in production side as well as in thermal sites. Though ANSYS 14.5 is used for the simulation purpose, and it's provide a numerical solution of partial differential equation governing airflow and heat transfer in discretizing form. So these are the some glimpses from my simulations tool. So ambient temperature, I'm taking the ambient temperature is 41 degrees centigrade, soil temperature is 35 degrees centigrade, and buried temperature is 22 degrees centigrade, and velocity is varies from 0.1 to 15 meter per second. So this data is for the, I'm taking this data for the simulation purpose. Now same as the analytical analysis, some effective parameter is here for the pipe material. So main consideration in selecting the material are cost, strength, corrosion, resistance, and durability is the main parameter for selecting the tube material. Now, tube material has a little influence on the performance. Selection would be determined by the other factor like ease of installation, corrosion resistance, etc. Spacing between the tubes should be enough so that the tubes are thermally independent to get the maximum benefit. In some cases, we are using some parallel pipe, 3 to 4 parallel pipe with the difference between two pipe is 1 to 2 meter. As well, sometimes we are using the single pipe or double pipe for the analytical or experimental analysis. So these are the in my first study, I'm using the copper pipe as a horizontal buried tube heat exchanger. The air inlet at ambient condition from through this blower, and air passes from this heat exchanger, which is buried at a buried depth. Length of the length of heat exchanger is approximately 24 to 25 meter, and the conditioned air is outletted from the heat exchanger at the ground level and pass into the building or room. So this graph is show the temperature as and with respect to the length of the pipe. So from this graph, the air temperature is approximately 40 degrees centigrade at the inlet condition, and at the outlet condition is approximately 25 degrees centigrade at the outlet of the heat exchanger. But some important thing in this graph, at the length of 15 to 16 meter, the temperature of air is constant at the from 15 meter length to the end of the pipe. So effective length of the heat exchanger is 15 meter. After the 15 meter, the air temperature is almost constant at the throughout the heat exchanger from the building. Same as the RCC pipe is used for the heat exchanger. So air is inlet at the 40 degrees centigrade, and outlet temperature of the heat exchanger is 28 degrees centigrade, where I am using the RCC pipe. Same as the PVC pipe, the air is inlet at 41 degrees centigrade and outlet temperature of the heat exchanger is 39 degrees centigrade, where I am using the PVC pipe. So the copper and RCC has a higher heat transfer performance compared to the other material. Air achieve 27 degrees centigrade and 28 degree temperature on a travel from 5 meter and 18 meter in copper as well as in RCC pipe respectively, as we shown in the graph. Whereas in PVC pipe, the air is cooled at 28 degrees centigrade. In PVC pipe, this is the graph of PVC pipe, the cooled at 28 degrees centigrade on travel of 25 meters. RCC and PVC have the compatible result from the temperature point of view. Length of the pipe required is less in case of copper and RCC. PVC pipe is more preferred as it has strength in soil and easy of installation. Some installation problem and some strength issues in copper and RCC pipe. So I am preferring the PVC pipe for the heat exchanger. From the analysis and the literature review, it is observed that the performance of the heat exchanger is not affected by material for the buried pipe. Therefore, a cheaper material pipe can be used for making the heat exchanger. Now, this is a comparison chart. The heat transfer rate at a various length of RCC, a horizontal buried tube heat exchanger at a different air velocity. Air velocity is a very important role of heat exchanger. The result represents the inlet and outlet temperature of air at a buried heat exchanger systems. Its comparison of result of simulation for the air velocity of 0.25, 1 meter, 5 meter, and 15 meter per second at the inlet of the heat exchanger. The increase in the temperature of air at the outlet of the heat exchanger due to the increment of the air velocity. Same as in PVC, the air velocity is varied from 0.25 meter to 15 meter per second, and this graph shows the inlet temperature and outlet temperature at a different air velocity, where I am using the PVC horizontal pipe for the heat exchanger. Now, vertical heat exchanger. The vertical heat exchanger overcome the limitation of horizontal heat exchanger, because in horizontal heat exchanger we require lots of land, and it is very difficult for the installations. So it's required vertical buried heat exchanger required a small space compared to the horizontal buried heat exchanger. In horizontal heat exchanger, approximately 25 by 3 meter space required for the installation of heat exchanger, whereas in vertical heat exchanger, it's simply approximately 3 by 3 meter space is required for the installation of a vertical heat exchanger. So a vertical heat exchanger is overcome the limitation of the horizontal heat exchanger. Now, CFD analysis of vertical heat exchanger. In vertical heat exchanger, the temperature is approximately, this is the condition for the winter. The inlet condition of the heat exchanger is 31 degrees centigrade, and the outlet condition of the heat exchanger is 41 degrees centigrade. Some CFD simulation of the heat exchanger here, and the 31 and 41. So approximately 10 degree temperature difference is in vertical heat exchanger, in winter conditions. Now, experimental analysis. Uh, from CFD analysis and analytical analysis, uh, all the values, all the result of the above analysis is validated from the experimental analysis. The CFD based horizontal and vertical heat exchanger modeling is validated by taking the observation on an actual horizontal as well as the vertical heat exchanger installed at my place, and observations were taken repeatedly, both in experimental as well as in the simulation. Flow of air is made through PVC as well as the RCC pipe separately. So all the observations were taken by 8-channel data logger with a calibrated sensor. So first of all, I find out the buried length and buried temperature for the experimental analysis. So I install one temperature measuring probe under the 3-meter depth from the surface for the finding out the buried depth, and it consists of 4-meter long, 50 diameter of PVC tube on which sensors are mounted. The probes has 4 sensors.
Excuse me, sir, your voice has stopped.
Hello. Yes.
Adi Patel, sir, your voice has stopped.
Soni sir, am I audible, sir?
Yes, sir, perfectly.
So this is the practical setup of temperature measuring probe. The sensors. Wait a minute, please. It's visible, Sony?
Yes, sir, it's visible, perfectly fine.
This is the practical setup of temperature measuring probe. The sensors are placed at 3-meter, 2-meter, 1-meter, and 1-meter depth below the ground. And one sensor is placed 1 meter above the ground for measuring the atmospheric temperature throughout the year. And one is placed just 2 centimeter or near to the 1 centimeter or 2 centimeter below the surface for measuring the surface temperature of this ground. After the installation of sensors, tube was filled with the granules of thermocol to prevent the convective heat transfer from one level to the another level. A bore was drilled and installed the probe, and the bore was taken backfilled by the soil. So this bore is built by some outer agency, and the temperature measuring probe I installed in this drill hole. Now sensor. The sensor is a PT100 type sensor is used for measuring the temperature under the depth of soil. This type of RTD, this sensor is a resistance temperature detector, and the temperature were noted at the 3 point with the interval of 1 meter to the 3 meter on hourly basis in each month, usually near the middle. Why I am using the PT100 instead of the thermocouples? A wide temperature range of PT100 approximately -200 to plus 850 degrees centigrade with one sensors, good accuracy, good interchangeability, long-term stability. When we're using the metals such as the platinum, they are very stable and are not affected by corrosion or oxidations. So other materials such as a nickel, copper, and nickel iron alloy have also been used for the RTDs. And this material are not commonly used as they have lower temperature compatibility and are not as a stable for the repeatedly as a platinum. So is a observation table and different data taking from the temperature measuring probe throughout the year, and I am taking the average of here showing the average of all the months throughout the year. So in month of January, the ambient temperature is 20 degrees centigrade, means it is a winter. In month of May, it is 35 degrees centigrade. It is the summer season. Now, the soil temperature at different depth. So, in month of January, surface temperature is 15.5 centigrade temperature. 1 meter is approximately 21 degrees centigrade. At 2 meter depth is 22 degrees centigrade, and at 3 meter it approximately 26 degrees centigrade. Same as in month of May or in summer season, the surface temperature is approximately 25.8, means 36 degrees centigrade, near to the ambient temperature. So at 1 meter depth is approximately 29 degrees centigrade temperature. 2 meter depth is 26 degree temperature, and at 3 meter depth is approximately 27, means 26.6 degrees centigrade. So from this observing data, or from this observation table, you easily show the approximate temperature at buried depth, means at a 3 meter depth, approximately a 26 degree temperature is constant throughout the year. And this energy is used for the cooling as well as the heating purpose of any building or the room. So from the temperature measuring probe, I validate the buried depth as well as the buried temperature. Buried depth is 3 meter and buried temperature is 26 degrees centigrade from this experimental analysis of my heat exchanger. Now, so graphically representation of this throughout year data of from the temperature measuring probe. The blue color line shows the ambient ambient air temperature throughout the year, and the red color line shows the temperature at buried depth. And the difference between this blue line and red line shows the cooling as well as the heating effect from the buried tube exchangers. So in month of May, the heat exchanger is used for cooling purpose, as well as in month of December and January, I am using this heat exchanger is for heating purpose. Now, the parameter of experimental setup of heat exchanger, the tube diameter, means outer diameter is 0.1 meter, inner diameter is 0.102 meter, A tube length without any fins is 25 meter. A buried depth is 3 meter. Air velocity is varies from 1 to 15 meter per second, and ambient temperature for the cooling is 42 degrees centigrade. These are average data taken for the designing of the actual heat exchanger. Now, first setup of my heat exchanger is made up by a copper, and the heat exchanger installed at my place. The heat exchanger is made up by copper. Now, some glimpses is some photographs for the installation of a copper buried tube heat exchanger. This is a horizontal copper buried tube heat exchanger. Now, the I am using the RCC pipe for the heat exchanger, and this is the picture of the installation of RCC pipe buried tube heat exchanger, horizontal heat exchanger. And here in picture, in middle of the picture, I put one sensor for measuring the temperature at the middle of the heat exchanger. So I am putting the 3 sensor. First one is at the inlet, second one is the outlet, and third one at the middle of the heat exchanger. These are the picture of the installation of heat exchanger as well as the blower of the heat exchanger. Now, these are the parameter for the vertical heat exchanger. Tube outer diameter same as the horizontal diameter. Same as the horizontal heat exchanger. Only one thing is varied. This is the vertical buried depth. This is 8 meter. In horizontal buried tube heat exchanger, the buried depth is 3 meter, whereas in vertical buried depth is 8 meter. Air velocity same as 1 to 15 meter per second. Yes, is any problem? Yes. So these are the parameter for experimental setup of vertical buried tube heat exchanger. Now, this is the design of vertical buried tube heat exchanger. One setup or one arrangement for the condensed water in vertical buried tube heat exchanger, because as per the humidity of our Indian climate condition, some water droplet is in this vertical buried tube heat exchanger, and sometimes it choke up the heat exchanger. So I make some special arrangement for this droplet or condensed water in air. So first of all, I make a bore of diameter 4 feet and depth of 8 to 10 meter. Then I install this vertical setup in this bore. The schematic diagram, and the second one is the actual diagram of vertical buried tube heat exchanger. Now, simple CPU fan is used for blow the air inside the vertical heat exchanger, and some sensors are put in this heat exchanger for taking the data, taking the temperature data inside the heat exchanger. So this is the final setup of vertical buried tube heat exchanger, and all the data is taken from the data logger. Now the result part. The result represents the performance of the horizontal heat exchanger with a different inlet air velocity with a different pipe material. Second result, I compare the CFD performance of horizontal as well as the experimental performance at a different air velocity. Third result, I shows the simulation of a vertical heat exchanger for summer cooling, experimental result of a vertical heat exchanger for summer cooling, performance of the vertical heat exchanger for summer cooling, and the comparison of performance of horizontal as well as the vertical heat exchanger systems. And finally, the psychrometric result of the system for the cooling as well as the heating. So these are the result of a horizontal buried tube heat exchanger numerically as well as the experimental. In numerical result, I am taking the 3 pipe material: copper, RCC, and PVC. Whereas in experimental analysis, I am taking the 2 material: RCC as well as the PVC. So pipe diameter, pipe thickness, pipe length, air velocity, ambient temperature, buried depth, and the maximum temperature drop. Up to a buried depth, almost all the constant parameter is used for the sorry. From pipe material to buried depth, almost all the parameter is constant for the numerical as well as the experimental result. But in maximum temperature drop is a result of the both the analysis. So 18-degree temperature difference is in copper pipe as well as the 15-degree centigrade temperature drop in PVC pipe in my numerical analysis. Whereas in experimental analysis, approximately 12 to 11 degree temperature difference, 12 degree centigrade temperature drop in RCC pipe. Temperature drop means the inlet temperature of heat exchanger and outlet temperature difference. So 12 degree temperature difference between inlet and outlet of heat exchanger in RCC pipe and 11 degree temperature difference in PVC pipe. And same is the temperature drop at 15 meter per second air velocity is 16, 14, and 11 in numerical analysis, as well as 10 and 12 degree temperature difference in experimental analysis. So this is the comparison chart for numerical and experimental result in horizontal heat exchanger. The result represents the temperature profile of air when ambient air passes through a buried tube heat exchanger. It is the comparison result of simulation of air velocity at a 0.1, 1, 5, and 10 and 15 meter per second with the experimental result of air velocity of 15 meter per second. So here the yellow color line shows the experimental result of heat exchanger, whereas the other graph shows other colors lines shows the simulation result of heat exchanger. The experimental result is almost same result with the CFD analysis. Now the simulation result of vertical heat exchanger for the summer cooling. This is the simulation result of vertical heat exchanger. Now the experimental result of vertical heat exchanger for the summer cooling. The blue color line shows the ambient air temperature for a specific time, means the month of April to 6 months, April to June. So blue color line shows the ambient temperature, and this the red color line shows the heat exchanger outlet temperatures. So here you shows the temperature difference between ambient condition and the outlet condition of the heat exchanger. The outlet condition of the heat exchanger is approximately near to the 30 degrees centigrade temperature. And I think it is a very comfortable condition in case of summer as well as in the winter. Now, the COP of the, the performance of the vertical heat exchanger for the summer cooling, so it approximately 3 COP in specific period of study. Now, this is a comparison result of performance of vertical as well as the horizontal heat exchanger. Many researchers say the horizontal heat exchanger is very convenient for the air conditioning purpose. In some researchers say vertical heat exchanger is very convenient for the air conditioning purpose. So here I compare the both heat exchanger at performance level. So the blue color line shows the atmospheric conditions, and obviously as per the graph, the blue color line shows the winter conditions, as well as the green color line shows the horizontal heat exchanger performance, and the red color line shows the vertical heat exchanger. Only one limitations of the both heat exchanger is the space. If you have a lot of space or many space for the installations, you can easily install the horizontal heat exchanger. And if you constrain some space, so you go for the vertical heat exchanger. So only I think space is a very limitation between the heat horizontal as well as the vertical heat exchanger. Now you say is a psychrometry chart. So cooling process, the straight line. So 1, 2, 3, and 4 state is so. 1 is the inlet condition, 2 at the depth condition at ground surface, 3 is the outlet of the heat exchanger, and the 4 is the room condition. So cooling, dehumidification, then again heating. So this is a psychrometric process of heat exchanger. Same as in heating process. 1, 2, 3. So 1, 2, 2 heat, 2, 2, 3 again heating. Now 3 to 4. So this is the humidification process. So this is the psychrometric process of buried tube heat exchanger in heating conditions. Now the conclusion of all the research. The convective heat transfer coefficient is increased, while time to which the air remain in contact with the ground is reduced. So this is a very important thing. The latter effect in dominant, therefore, the less drop in temperature is obtained at air velocity is 15 meter per second than the 1 meter per second. So at higher velocity, through the drop in temperature of air is less, at the total cooling effect achieved per unit time is much more. So it is easily and well defined in our concluding chart. It can be seen that the maximum temperature drop occur at velocity at 1 meter per second. Obviously, if air velocity is low, we get the maximum temperature drop. If we go for the higher velocity, so minimum temperature drop is occur. The maximum temperature drop for the RCC pipe is 18 degrees centigrade in numerical analysis, whereas 12 degrees centigrade in experimental analysis with the same pipe length. So this is a conclusion table for the earth tube heat exchanger, the numerical result as well as the experimental result. the design parameter, means pipe diameter, pipe length, air velocity, and air temperature, air ambient temperature is constant for the both analysis, numerical as well as the experimental analysis, where the ambient temperature is in numerical condition is I'm taking the 26 degrees centigrade. In experimental setup, actual temperature is 16 degrees centigrade in winter seasons. Buried depth is same. Horizontal is 3 meter. In vertical, the buried depth is 8 meter. So maximum temperature drop. These are important or our main result of both the heat exchanger vertical as well as the horizontal. So from numerical result, numerical analysis, the maximum temperature drop is 18 degrees centigrade in horizontal buried tube heat exchanger and 11 degrees centigrade temperature drop in vertical buried tube heat exchanger. And I validate both the result, horizontal as well as the vertical, in numerical analysis. I validate this result in experimental analysis. So I am getting this 12 degrees centigrade temperature drop in horizontal buried tube heat exchanger and 10 degrees centigrade temperature in vertical buried tube heat exchanger. So I validate numerical result with experimental result with minor difference. There is a fair agreement between the experimental and the simulation results. The maximum variation observed is 3 to 4% here. So here some temperature difference between numerical as in experimental analysis. So it is approximately 3 to 4% variation in both of the result, numerical as well as in experimental. Delta, that means the temperature difference, is found to decrease with increasing the flow velocity. Now, the performance of the heat exchanger is not affected by the materials of a buried pipe. So, as per the experimental as well as the analytical and CFD, so much more difference in the temperature by the material. So the cheaper material and easy for the installations can be used for the making the heat exchanger. So I'm taking the PVC pipe for the heat exchanger. The horizontal heat exchanger of 25 meter length and 0.110 meter diameter, temperature raised to 10 to 12 degrees centigrade has been observed. The COP of the horizontal systems varies from 7 to 8. The performance of vertical buried tube heat exchanger was investigated experimentally, and the vertical heat exchanger occupied the less space compared to the horizontal. And experimental results indicate the 8 to 10 degrees centigrade temperature difference, whereas the depth of the bore is 8 meter. So in both of conditions, horizontal as well as the vertical, the buried depth is only basic difference or base input difference. In horizontal condition, I'm going only up to 3 to 4 meter, and in vertical condition, buried depth, I'm taking the buried depth is 8 to 10 meter. So simulation and actual results are almost similar. The COP of the vertical heat exchanger varies from 4 to 6. The heat exchanger rate of the two type of heat exchanger with a different operational mode, such as the air velocity, different pipe material, and continuous operation mode have been investigated. The heat exchange rate were investigated numerically using the commercial CFD software is Fluent. In this research, the heat exchange rate from experimental data are also presented. The numerical result shows the reasonable agreement with experimental result. Small difference between numerical as well as the experimental result were caused by several uncertain factors such as a local ground thermal property, because the local thermal property, ground property is a major role, play the major role in the performance of the both heat exchanger. Second one, the boundary condition is also important for the designing the heat exchanger. And the last one is the initial condition. The input parameter is some factors for affecting the performance of the heat exchanger. The deviation of the heat exchanger rate between the experimental and simulator result in range from 5 to 15% for the vertical heat exchanger and 10 to 15 for the horizontal heat exchanger. So is a range for deviation 5 to 15 vertical and 10 to 15 for horizontal. The buried tube heat exchanger with a porous insert can be, so these are the feature scopes of my research. Some porous material can be used for the better performance. The heat transfer can be improved by incorporating the different type of twisted tap configuration. In this research, I am taking only a simple pipe without any fins. So simple pipe is used for the heat exchanger, but we can use some different type of twisted tap or some parallel pipe or multiple pipe is used for the performance. The system can be studied for the effectiveness by using the various working medium. So here I am taking only air is a working medium, but we can use water and other working other material is used for the working medium. The effect of a nanofluid enhancing the heat transfer in buried tube heat exchanger system for cooling and heating application in building can be attempted. So my research is funded by East Coast. So I'm thankful to East Coast for the granting my research project. I published one patent on my research, the high efficiency combined air conditioning systems. Thank you all. If you have any doubt, you can free to ask, please.
If any participant has any question regarding this topic, he or she may ask question. Sir, I want to ask one questions that I am getting in my mind. Is there any real applications of this BBIT exchanger in Gujarat currently? The mic is mute, sir. Your mic is mute. So please on your
Sir,
mic.
your mic is mute.
Yes, am I audible?
Yes,
Yes.
yes.
Yes, sir. The actual application and actual heat exchanger installed in Ahmedabad Zoo for the animal for the air conditioning purpose, and another system is installed in Vadodara municipality sport complex, and I designed this entire complex for the air conditioning purpose, and with the help of some outer agency, I get actually not 100%, but some partial application is installed in Vadodara Sports Complex. So in my knowledge, two application, one is in Ahmedabad and second one is in Vadodara. From Modi sir, which pipe material can be preferable for the residential purpose? From my research, actually copper and RCC is very suitable for the heat exchanger performance, but due to the installation and the strength of the material, we can use PVC pipe for the heat exchanger. So PVC pipe, I think, very much easy to use and for installation of this heat exchanger. From Santosh Vyas, it is widely seen that the PVC pipe are used in BTHE cooling system, but this material is very poor in heat transfer. Why any metallic pipe is not preferred? Good question, Santosh sir. Some metallic pipe is some corrosion, and due to the some strength problem, PVC pipe is very suitable for the heat exchanger. And after some time, as per the thermal gradient equation, the no pipe material affect the performance of the heat exchanger. So PVC pipe is very suitable for this heat exchanger. Okay,
Thank you, sir,
Santosh,
for giving the answer.
more question?
Yes, any other participant want to ask questions, please?
I think this topic is, I think, some very different from our knowledge. So I don't know. I easily आपको मैंने समझा तो नहीं कि समझाई सक्यो कि नहीं समझे, but it is very new for all the researcher and mechanical engineer. So thank you all. Thank you. Yes, here.
Yes, thank you, sir. So, R.D. Patel sir has delivered such a nice informative session on the earth energy topic. So, on behalf of these participants, I would like to thank you, sir. And if the participants, it is actually an online training, but if it would be an offline training, then participants would be able to see this whole working model of BBIT to BBIT exchanger, which has been installed by the R.D. Patel sir in the campus of BNB Institute of Technology, Vidyanagar. But if anybody wants to visit that project anytime, he or she can get the consent from the R.D. Patel sir and see the working model of this BBIT exchanger. So, on behalf of BNB Institute of Technology and organizing team and participants, I extend my heartfelt gratitude to Dr. R.D. Patel sir. We really appreciate the work done by you, sir, in the field of BBIT energy for conservation and energy conservation and management. We are grateful that you have shared your research work with us, and I am sure your work will act as a guideline for all those who are interested in research in this field. Once again, thank you very much, sir, for delivering such a nice and informative session, sir.
Thank you all. If you have any query, please mail me or direct contact to me, so I can give any answer related to my research. Thank you very much. Thank you all. Thank you, Hirar and Joseph. Thank you very much.
Now, I would request all participants that we are leaving for the lunch break, and we will meet at 2:45 p.m. So we will start our next session at 3 p.m. sharp. Okay, so please be ready at 2:45 p.m. and get your access in the Google Meet. Thank you all.